So if our first talk was the rocky road, so perhaps now we have the long road. A tutorial with one part now and the second part after the lunch break. It's a pleasure to introduce Reisig to you. He's only the chair of Theory of Programming at the Humboldt University in Berlin. And he will take us to this journey on formal methods for service-oriented computing. So I'm looking forward to your tutorial.
Okay, thank you for the introduction. So we learned this morning that to save energy is a good point. So I thought I could sit on the chair and save energy. But I will not do that because I think it's not so polite. So you may sit on your chair and I will stand. Okay, so before I start to tell you what I intend to tell you, I have made a small prelude, so to speak, and it's called In Praise of Models. And some quotes, I think you will know these quotes. Butch, who is the inventor, one of the inventors of the UML, said models should become a first-class citizen. And that means they are not yet a first-class citizen, but they should become one. And at the end of the day, we should have no longer software houses, but we should have model houses. So what you produce and what you sell are models and not software. And we should have, in analogy to open software, we should have open models. And there's even an initiative called Open Models Initiative to collect a set of beautiful models. So models are important. And now what I did these 2 days, I was asking me what is the role of models in this summer school? Do we see here models of software or models of systems? Do we see many data models or behavioral models? And so what I did, I came Monday afternoon only. I started in each talk to look, did he say something on models and what did he say on models? Okay. Unfortunately, Monday morning is not included. I'm sure there was said a lot of models and it would have been nice to include that too. But I think I have got a decent view on the actual use of the term models. Okay. So on Monday afternoon, Uwe Breitenbücher said, asked how to model. He had these beautiful prepared questions where he asked a lot of, and in the middle of that he asked, how should we model all these things? And that's a good question. And then I learned binary is a tool to graphically model Tosca topology and planes. So apparently a model is a graphical representation of something, which is fine. And then in the internet I found what a topology template is also referred as a topology model of a service. So it defines the structure. So a model is apparently something that defines a structure. And we come later on a little bit onto this point. And on Tuesday, we learned Pablo is writing, I'm sorry, I just moved this a little bit. He has a modeling tool to write service level agreements. So a modeling tool that makes models for service level agreements, and I talked with him because he also said he would formalize real agreements on document. And formalization, that is another part of models. So there are formal models. And I'm interested, and we'll talk about formal models. And I asked him in the break if he is really serious about formal, and I learned he is. You see here. No. He is serious because he really uses logics to represent documents. And in addition, and then comes the other important aspect of models, that you do not only want to model documents or things or states or structures, but also behavior. And the term of behavior is becoming more and more important in modeling. So he also has a little bit a grain of things saying, first is this the case and then is that the case. So to have some development specified also in the model. Okay, but also what else did we see? Holger Schwarz spoke about simple as workflow modeler, okay. And Sebastian Lang then spoke about model-driven development. And that's an interesting point. So he even spoke about logic component, but it turned out logic is only a phrase here, and there was no logic at all. A model in his context was a structured or a graphical representation. So that was something informal again. And then he said, in a say provocative way, that modeling is not so good because the effort is greater than the risk. So let me say it a little bit more concrete. The effort to construct a model is bigger than the gains that we obtain by the model. So if we construct a model, we have an effort to do that, and I'm always, okay. And then we want to gain something from the model, and apparently a lot of people think what we gain is not enough. It's not worth all this effort to construct the model. Therefore, they don't model, and then he said, try and pray is the solution to build software nowadays, which of course from a scientific point of view is a disaster. But still it seems to be the case that this is how it's done. So now let's look at this inequation, and we could ask, how can we improve this inequation? Well, how can we reverse it? First we could make this smaller. Is this a good idea? So to invest less in constructing models. I think this is not a good idea. The way we construct models is we have to think in our head what we want to express, and then to express the model is not such a big issue. But thinking about the model you cannot improve. To think less or quicker or less deep, that is not a point. So I think the right thing is that to reverse this, you must increase the right side. So what you gain from the model must be much more in the future than what you gain so far from a model. The question is, what do we gain so far from a model? I think what we gain so far is we get some clarification of our thoughts. So you write a model, usually some boxes and some arrows. I saw on the posters, by the way, some models with 7 kind of different arrows. And maybe if time I would like to ask the modeler what is the meaning of the 7 different kind of arrows and of 5 different kind of boxes and squares and circles and whatever. So this kind of models is more an intuitive thing, and you explain a little bit to somebody else what you think should the software do, and that is the role of the models. So to make it clearer a little bit. That's a nice thing. I don't say anything wrong with that. But if this is all what a model could be used for, then indeed I agree that to construct this model is a huge effort for a small gain.
Sorry.
Okay.
I wouldn't say it's a structured representation. I would follow the style of the definition of model.
Okay, I agree. Of course, I'm coming to that. Yeah. But in our context, I would not have this general view of this. So in our context, I think we also want to verify in terms of the model. So we have an idea of the system, we have an idea of the properties of the system that the system should have, and the model should help us to prove that at least the model has the properties we wish. And this verification problem is, of course, a big issue. And the second point is that would help us to use models is to generate code out of the model. So you refine the model for a while, and at the end of the day you have a model that more or less is software, more or less can be run automatically. If you have models that serve you those 2 issues, then I think it's worth to make the model, because modeling and programming then is almost the same. Okay, and that's the long perspective. I'm happy you agree with me. Fine. Okay, so summing up what I've seen so far, and this is an aspect here, modeling mostly refers to static structures. I've seen a little bit of models that describe development or steps or whatever, but most models that I've seen in this 1.5 day are static structures. There's nothing wrong with static structures, but this is only part of what we intend to model. And static structures, by the way, it databases is dominated by the relational data model. So modeling data and modeling structures is anyway an issue that is very well known. And what we need is modeling of behaviors. And modeling of behavior is also done, but it's rarely done, and it is much more difficult and much more unclear, and there are much more approaches that are not related to each other. So this is the field that I'm interested in. And now I can tell you what I intend to tell you. I intend to tell you something about behavior modeling. So static models, data models, that is done in many talks in this school, and I will glance not all, but many relevant modeling techniques for behavior. Okay. So, I give you a survey, and here I didn't write formal models, but even I did write formal methods. Maybe you know there is a European conference series that's called formal methods, and I refer a little bit to that. But I will show you a lot of, but I start with modeling, formal methods. At the center of formal methods stands modeling, but in addition, as I have said already, stands also analysis of models, and at the end, design of systems. So I will talk a lot on modeling and a little bit on analysis, and this design issue, the software engineering issue on how to use models to small models and to construct big models, etc. I will glance this, but not talk too much about this. Okay, so I slowly fill in this slide. The slide will be here very long, and it will grow more and more, and I will say something to every model I talk about. We start with an extremely simple observation, that is the most elementary thing we do is discrete steps. This is not at all trivial that we start in informatics with discrete steps, because science for centuries had another kind of modeling behavior. So in physics you usually had the x-axis that was the time, and the time counted in real numbers. And on the y-axis you had some values that changed over the time. So that is the way that modeling of behavior was done for very long. And by the way, I recently learned from biologists who start now to make a theoretical biology, and systems biology as they call it, that they also for very long had this kind of modeling with differential equations, and the development of plants or of anything, of chemistry, of living chemistry was modeled this way, and they are now changing to the world of discrete steps. And it's very interesting what they are doing. I feel this, I'm happy. So discrete steps are the fundamental thing of our behavioral models. Okay. So if you have one if you have one discrete step, so something A can be done, you can press a button, and you say the initial state, you press a button, you have the resulting state. You don't speak about time. You don't say it takes 5 milliseconds or 5 hours. You just say initial state, final state, step in. So if you have a step, you say A step, then you can maybe execute the same A step several times, or you don't have only A steps, but A, B, C steps, whatever, then you have many steps. And a behavior or a run of a system is a set of step occurrences. And in the moment I say it's a set. In a minute I will say something more about the set. But the first question is it finite, is it infinite? And well, in the classical world, in the way we have all been educated, we say it's always finite, the behavior will eventually end. And in this world we are in, the service world, we realize that this is in general not finite. Behavior will not stop. And it's much easier to speak about infinite behavior, and even many models that I will show you say in principle everything is running in at infinite. And in case you want a model to present something finitely, you just say after a while the steps will not change anything. So it's easy to have it always infinite. But if you prefer finite, it's fine. One must be clear, is it finite or infinite? More interesting is it a sequence? Is it a sequence in time? And suddenly we smuggle in the notion of time once more. And that's what we learned for 50 years of informatics, that behavior is a sequence of events or a sequence of discrete steps. And as I will show you that this idea of a sequence seems not to be so good in all contexts, and especially in our context. It is no longer very reasonable to implicitly always assume that the system jumps from global state to global state. And as a provocative question, I can ask you, so take the internet, which is the actual state of the internet, and which is the next state the internet does? Okay, is this a reasonable question at all? So is it really useful to assume that the internet is in a given global state and makes the next state? And some of you smile and some of you say no. And that shows in the small worlds which we started informatics, that was reasonable to have a global state and this kind of steps. But the kind of abstraction that we are doing with this is so difficult or more and more inadequate the bigger the systems become. And I think we all agree that the internet is not in a global state and does not make a next step. But there are many independent components, and to order them artificially into a time scale is so unrealistic that we should get rid of this. This is a difficult thinking, I know that, but it's not difficult because the contents is really difficult. It's only difficult because we all have been taught, we all have been educated, so to speak, in the wrong way, in the way that we consider sequences of steps as the normal case. So we must learn slowly that a partial order of event occurrences is what is useful. And we will see later on that this idea helps a lot. For instance, to compose to a given system something else, it's much easier that you can say the given system remains as it is and then put something else, and if this is in the partial order composed, and then it's easy. Okay, we will talk about this. Well, a system. So far I said you have one step, a behavior is a set of steps, a sequence or a partial order of steps. So a system as a whole system may have many behaviors, and these many behaviors, again, you can question, is the system really fully described as a set of behaviors, or do you need some more information? But in the classical world, it's a set of behaviors. It's most natural, it seems to be most natural. And again, here I would say you need some more information. You need more information about the branching. So where do one have two behaviors, the same initial part, same prefix, and then they branch. And I will show you very concrete examples where this branching idea is crucial. Okay, so you see, I try to prepare you to get a little bit familiar with the idea that what you have learned so far, sequences of behaviors, a set of sequences describe the system, is no longer what we are interested in. It's also a notion of event structure relevantly, which I will not go into details. I assume nobody has heard of it. Okay, so how do we represent a system? And there are two kinds of representations. One that's a little bit an artificial classification, but I try to make some classification here. So some are represented like automata, more or less, and others more like grammars. And let's go to the automata style. So the neutral version is transition systems. And the term transition systems is very simple and helps a lot, but doesn't help everything. So the transition system is just, you can say it's a graph, and the nodes are the states, and the arcs are the steps. And some of them have one initial state, some have a set of initial states, some have final states, some don't have final states because the sequence of path through the graph runs infinite. Some are finite, some are infinite. So the term transition system is just generalizes what you know under the name of a finite state automata. Okay, the next thing I've mentioned here is petronets, and now I tell you the style of presentation I will do here. I will show you a lot of modeling techniques, But I will not show you PetroNet looks like this and that looks like this, so I will show you a lot of things which are not so relevant at the moment. What I will mention and why I have chosen the forthcoming choice of models is that each of these models has a specific property why it has become so relevant. And for each of these models that I will tell you is, I will make one remark what this model can do particularly good. Okay? So what is the point? What can PetroNets do better than others? One idea is that these sequences of behavior that I spoke about here, sequences as a behavior is no longer in the center of the thing, but this partial order idea is in the center of PetroNets. There are some other points crucial, but the partial order of one behavior is a partial order of event occurrences. That is interesting in the context of PetroNets. Then I have mentioned state charts here. I assume many of you know state charts suggested by David Terrell. And there one idea is that you can specify hierarchies in an interesting way, and you use it now as a graphical representation. It's very beautiful that you can say, I have a system with a lot of states, and now I want to specify in whatever state you are, now this happens. For instance, you have a system, an electrical system that television or whatever, it may be in many different states, but when you unplug it, when electricity stops, then you go out. And in classical, say, automata world, you have to enumerate all the states. So from this state, you go out, and from that state, and you have to enumerate all the states. And in state charts, you can avoid that. And to avoid explicit enumeration of all the states reachable, that is an important point in the context of distributed systems, simply because quickly there arise so many different states. We will come later on to this point. By message sequence charts, live sequence charts, that we have even seen some examples here yesterday. They were not called this way explicitly, but implicitly. So you have threads of behavior, some fixed number of behavior threads, and they eventually sometimes send asynchronously messages. Okay? Then, of course, you can also model PetroNets, but you are not refined to the structure of a set of fixed sequences of control. And I have the impression that some people too narrowly consider distributed system always structured in this way. So, assuming you always have a fixed set of threads, which are in each thread is sequential, and they send messages. This, of course, is a lot of concurrency involved, but that's not the only structure that concurrent systems can consist of. Parallel programs are all like this, so many are like this. And here you have some other aspects, this live sequence chart, which I don't go into details. Business process modeling notation, or as Frank Lyman is not here, always says this is called business process modeling and notation, because now it's dot 2. And the end is very relevant. I must confess, Bernard may help me, that I don't really see the difference with or without and, but it is very relevant. Okay? So what is a BPMN model? I hope Bernard does not listen, and then I tell you the secret. It is a kind of PetroNet with some additional figures on. Okay?
Frank's research staff members take notes. I guess they record you.
Okay. Yeah. So, okay, next is chemical abstract machine, which I will not talk about because this is a model that is not relevant at all in the context of service-oriented structure. It's a completely different kind of distributed structures. But I say, you have something like a big pot, a soup, a big pot with a lot of elements in, and sometimes two of the elements can meet, and then they do something together, and then they disappear again. It's a completely different model, but it's also a very interesting model for distributed systems. Then come time automata and hybrid automata. They do include again what I ruled out initially, namely real time. So they say, well, sometimes you need the differential equations, and we have seen yesterday here also some examples where we say it's good to have differential equations to model something. Of course, it's good for some purposes. And these automata are combining, so to speak, the discrete states which are in real numbers, those states where the natural numbers are hit, and the rest is differential equations. Okay, so I just compiled this as typical representatives of automata like specifications of discrete systems. And the next is grammar-like, and the most famous kind of structure that is grammar-like is process algebras, and in our context it's mainly the pi calculus that became prominent for a while. And I tell you a story. So about 10 years ago, Frank Lyman phoned me and said, I have to know what a pi calculus is. I have no idea what it is. I visit you next week. You have 10 minutes. And then I had to tell him within 10 minutes what pi calculus is. It would have been easy for me to tell him this in 2 hours, but he wanted to know it in 10 minutes. So it was a challenge, and I think I succeeded more or less. So what is it? Process algebra is the idea that you have terms, like algebraic terms, and each term represents a process, and then you can play around with the terms. You can add them and not subtract, but add them, and you have several composition operators and rules that describe steps, so that a big expression can be made smaller, like in computing with numbers. But of course, you have also mechanisms that make smaller expressions bigger. So you have equations that you say the process X can behave as blah blah blah, and then comes bigger. So you have terms that become smaller according to derivation rules and bigger according to defining equations. This process algebra, and it's very frequently used, and it may be a good idea that also in our community we should use it a little bit more. And pi calculus is a special variant of this, where you have in addition some kind of information moving around, and the information is not just simple data. There are a lot of process algebra with simple data, but the information you can move around is the name of other processes. And then you can do what we in SOA have in this triangle, where we have a provider and a requester and a broker. And the idea is always that that a requester needs the name of the provider, and he gets the name from the broker. And after he's got the name, he can directly communicate with the provider without speaking anymore to the broker. And this kind of name dropping and name telling, and then with the name you can directly compose again in this style of algebraic terms with somebody else. That was the pi calculus. And the reason why Frank was so fond of it was that the people language should have been given that time of semantics, and somebody, I don't know, either IBM or Microsoft had a proposal using pi calculus. And in the standard there is also still, I think, some remarks of the pi calculus. Okay, pi graphs. It's like process algebras, but they exploit again, like state charts do, the space on a graphical representation. So you make a circle around something and say this is an area which is close together, and you have explicit communication to other such areas. Don't go into details here. Okay, now again I have made a more or less artificial separation. Now, so far, say until here, I spoke more or less about form, about discrete, about control structure. Let's call it control. I did not speak about data. Of course, all these models also have extensions that include data, but they are mainly made to represent in a finite way infinitely many control aspects. And now I talk about some other models where data are more relevant. The distinction is really artificial, but I didn't want to make a list of 30 things without any structure. Okay, so the first one is algebraic, I'm sorry that it's so long, it's algebraic specifications. What is this? In a way, it is classical first-order logic. You have a signature that is a set of symbols that are structured in a certain way. A set of symbols from which you can build terms, like in algebra you can build terms, and then you have the notion of a model. Well, that's very confusing now. In logic you have a notion of model that has absolutely nothing to do with what we here call a model. Okay? Still it is the standard term of model, and they have been much earlier than we, so they have the right to choose what they call a model. So a model in the logical sense, and I think you must always be aware of that this is not our model notion. So in the logical terms, they say you have a syntax, that is the terms, or the formulas, and then you ask, give me a structure where you have an expression, and you ask, give me a structure where this expression holds. Okay, and the model of an expression is a system, the structure where the property holds. So you describe a property, and wherever the property holds, that is a model of the formula. Okay? This is what logicians do, like it or not, but be always aware, if you, in the context of logic, if you read the term model, be careful if they mean our model or the other way around. Because usually we make it, frequently we make it different, the reverse situation. We say we have the real world, that is a structure, and then we want to model the structure in terms of abstract representation of terms. So we would say the terms are the model of the structure. But in logic they say what we are given is the syntax, and the model is the instance, something that is in real life, and that is where the model, where the syntax is valid. Okay, so be careful with that. There is this alloy specification technique. It's from the MIT, and they exploit an interesting observation. So, independent of how you model and what properties you are interested in, take any of your representation techniques and any property and assume the property is wrong. So you have a system where you assume a certain kind of property and assume the property is wrong. In the set of all models, the set of all models you have in mind, the property is wrong. So now comes the point. If the property is wrong, there's usually a small example where the property is wrong. Of course, as a mathematician, you can construct so crazy properties that the smallest counterexample is big. But usually in practice, if you do something faulty, if the system does not what you intend to do, then you find a small counterexample. And that's what they exploit in this alloy mechanism. So you have a specification of a set of something which has small and big examples, and if the property you claim is false, then there exists a small example. So they try systematically all the smallest instances, and they find quickly the counterexample if there exists one. Okay. Next is abstract state machines, as introduced by Yuri Gurevich in Microsoft. He's now in Microsoft for 10 years. I will tell you a little bit about this. That looks like a miracle. At first glance, it looks really like a miracle. Because what he can do is the following. He can model any system you have in mind in the most precise way you can imagine. So that really sounds strange, and I go a little bit into this. He says, whatever you consider as, well, you choose the level of abstraction. And that is, I think, the fundamental thing in modeling anyway. In programming, the programming language gives you the level of abstraction. The programming language tells you which operations you have. In modeling, you choose the level of abstraction. And abstract state machines say, you are free to choose your level of abstraction. Whatever you consider a state is also a state in your model. And vice versa. What in the model is an abstract state is also a state in your system. So whatever you consider a step, a single step, is also a single step in the model. Okay? And there you see that you are have fully freedom of abstraction. And what he claims with abstract state machines is that whatever system you have, whatever abstract level you consider, whatever you consider as one step, he also can model as one step. Okay. So there's one modeling technique that fits all the choices you can make. So that sounds extremely surprising. And of course, he is not a magician, but he is a good logician. And in his former life, he was a logician. And now I'll tell you the secret how it works. So he starts out with first order logic, as we all know it, or as we all should know. And there you have a lot of constant symbols and function symbols. And then he says, you are fully free to interpret the constant and the function symbols as you wish. So there is not a single symbol predefined or pre-interpreted as something. So you can interpret, or you have, not only you can do this, but also you have to interpret every symbol you use in a concrete way. I don't go into details. I would love to teach you this for 2 hours, but I will not. He's looking to me. So this is really an amazingly interesting thing. And one example I will give you what you can do with it. So there is a famous algorithm called echo algorithm. Don't know this. So the idea is the following. The first point is already crucial. Given any network, so given any network of processors, so you have many nodes, and every processor has a set of neighbor nodes. So every processor you can consider as a graph, where every node in the graph is a processor. Okay, and every processor has a set of neighbors. And now one processor is distinguished. He is call it the root or the source. So he wants to send out messages. I tell you what he does. He sends messages to his neighbors, and then he's waiting. After a while, each neighbor sends a message back, and then he's finished. And I tell you what every other node does. So if you are one of the other nodes, you may get a message from one of your neighbors, and you call him your parent neighbor for some reason. And then you do the following. You send messages to all other of your neighbors, and then you wait. And after a while, all the other neighbors send you a message back, and then you send to your parent message, to your parent node message back. That's all. That's the whole algorithm. And the point is, how can we model this? So we have to start to model given any network. So in a classical way, we cannot even say given any network. Okay, so we need something that is more liberal as usual. And the trick, of course, is that you have a symbol, network, neighbors of something, and the symbol n you can interpret in any concrete network. So in a way, this algorithm does not function on a network, but it's a schema that functions on every network. And what you need to express is any neighborship relation. And in addition, you need the quantification for all neighbors. You need the all quantum to express it in the specification. And we have rarely specification techniques that systematically allow to express quantums like for all that exists. And that you can do with abstract state machines. Okay, I will not go into it. For instance, then you want to prove whenever the initiator, this first node, is terminated, then every other node has reacted. How can you prove that? Okay, you can prove it on the schematic level in terms of pure logical deductions. And this is the fine thing with abstract data machines. Okay, then comes the node B. Some of the techniques are very small, B and Z. B is Abrial in Zurich, and in a way he's algebraic specification plus something. It's also common algebraic specification language was an attempt to unify all these algebraic specification techniques with little success so far, but maybe after some time this will succeed. Domain-specific languages I don't talk about a lot. Focus. Focus is an idea by Manfred Breu in Munich, and the essential, I give you an example of what he's doing. So assume what a buffer is. How would you specify, how would you model a buffer? And he suggests the following. A buffer has a stream, an input stream, an input port, and an output port. In the input port, there comes a stream of data. And in the output port, there goes out a stream of data. So a buffer, the infinite input stream, eventually goes out to the output stream. In a way, it's the identity function. The input stream goes to the output stream. But intermediately, if you stop it intermediately and look at it, then you say the output stream is a prefix of the input stream, and the rest of the input that already has gone into the buffer, but has not yet gone out of the buffer, that is inside the buffer. Okay, very interesting problem, how to specify this. And now comes something else. Now assume you have a faulty buffer. You have some kind of fault that can occur. So you may have a faulty buffer, and then you have a repair instance that you can define what means to repair the faulty buffer. And then what you want to prove, what you have is a proof technique that you can easily prove that the faulty buffer composed with the repair agent together are exactly a buffer. Okay, so this compositional proof is the crucial point. So what we always want is to say that a composed system has the properties of a composed system is a composition of the properties of the components. These are long-range aim. And so far we have not succeeded very much, but Focus did it in a certain way. And you have to pay a big price for that, but it is one of the few successful attempts in this direction. Okay, next is Sample Logic of Actions by Leslie Lamport. Leslie Lamport is famous for this and that, I don't talk about the other things. He's also, what he considers personally the most important contribution he has done is Sample Logic of Actions, which rarely anybody knows. And maybe I just give you an example of that. So if you have to specify a clock, an hour clock. So I'll tell you what an hour clock is. It's a cyclic behavior. It starts with whatever, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, and then again 0. Okay, it's cyclic. It doesn't have to do anything with real time. It's just a cyclic behavior, a cycle of 12 states between 0 and 11. Okay, this we call an hour clock. Now the next topic is it's only a technical example. The next thing you should specify is an hour and minute clock. So what is an hour and minute clock? For instance, it has the state 11:53, and then comes 11:54, 11:55, etc., and then 0, 0, and then 0, 1, etc. Okay, that is an hour and minute clock. So what we intuitively assume or expect is, if you are given an hour and minute clock, then it's an hour clock. For instance, if you go to a shop and say to a clock shop and you say you want an hour clock, and he tells you, well, I don't have hour clocks, I only have hour and minute clocks, and I give you an hour and minute clock for the same price, then you would accept it. And the idea is, in the hour and minute clock, if you only want the hour clock, just glue, to put a piece of paper on top of the minutes, and then you have an hour clock. And the problem is, with our specification, it's wrong. Because suddenly, this changed hour and minute clock shows 60 times the number 10. And then it changes to 11. And then there are 60 steps of 11, and then it goes to 0, etc. Okay? So we expect a kind of refinement or abstraction, which is intuitively so obvious, and which in our formal model doesn't function. Okay? So how should we model a stupid thing like an hour clock and an hour and minute clock in a way that refinement is preserved as we expect? That's the problem addressed in TLA. Again, the solution is more or less convincing, and I don't go into the details, but to have refinement and abstraction as a simple operation that is behind them, and that we should also achieve. Okay, pattern languages, I don't go into details. Pattern schemata, with that you can do what I have described in more details, also with abstract state machines. I don't say anymore. And that, maybe you know, it's another version of algebraic specification. So I think this was all my modeling stuff. And why did I choose, say it again, why did I choose this set of modeling techniques? Because I think all problems addressed in modeling techniques are addressed in this choice of modeling techniques. If you have some others, there are many others which are also interesting, but I assume that you would not find one that addresses a fundamentally additional aspect that is not addressed by this choice. Okay. Next point was analysis. And analyzing formal systems, formal models, you run immediately in problems of decidability. If your modeling technique is too expressive, you are immediately too incomplete, and some people are so proud that they are so expressive, which is such a nonsense, because in the moment you are too incomplete, you cannot deduce any property. Okay? So there is with too incompleteness always comes the theorem of Reis that says not a single property is solvable in general. Okay? So it is very interesting to have modeling techniques that are not too incomplete in order to get analysis techniques. And classical patterns, by the way, have exactly this property. They are not too incomplete, and that is good, because then, therefore, a lot of properties are decided. Okay. Yeah, the role of first-order logic. Why on hell is first-order logic so important? Everybody considers this the most relevant thing. And now if you look into the literature, you find so many different calculi, and all of them are called first-order logic. So with what right are they all called first-order logic? Did you ever think this way about first-order logic? So I tell you what first-order logic is. Again, you are in the spectrum of being expressive, but you cannot prove anything, and being less expressive, and you can prove a lot of things. For instance, propositional logic is not very expressive, but you can decide any question you put. And first-order logic is, in a sense, the right compromise. It is as expressive as possible, such that you can still do something. And what is it what you can do? Can you decide, by given a first-order formula and a question to it, can you decide if it's true or not? No, you cannot. So therefore, we have a general rule of saying an expression is logically true. You cannot decide this. Therefore, it's too expressive. But if somebody comes with a proof, or he claims he has a proof, and he shows you, I can prove that this is a valid formula, then you can discuss with him whether or not this is a proof, and at the end of the day you can objectively decide whether or not it is a proof. Okay? And every formalism that has this degree of expressiveness, that's first-order logic. Okay? So you can objectively argue about proofs, about claims, but you cannot decide them in a general way. And that's why first-order logic is so interesting, so important. And now that there exist hundreds of versions to write this down is not so relevant. Okay, the next point is temporal logic. And in our context, temporal logic is very important. So what is temporal logic? In the afternoon I will talk about this in more detail. Temporal logic is a sin. It is a sin in the context of first-order logic. Because in first-order logic, all the beautiful theorems on first-order logic assume all the symbols you use are not interpreted in a special way. That's the argument why abstract state machines are so interesting. The same argument. But in first order logic, you are allowed to do one sin. One sin you are allowed, and that's the following sin. You may choose one symbol and declare it as equality. So first order logic with equality is still okay. Not 100% okay, but 99.9% okay. It means you can still decide everything you want. It's a little bit more difficult, but you can say two things are the same. And this comes not so much as a surprise, because we say in philosophical terms, you can say equality is the only universal relation in the world. So whenever you have two things, you can ask, are they the same or not? Or two descriptions of things. For instance, the famous example is that somebody sees a star in the morning, and sometimes it comes in the morning, and somebody else realizes there's a star sometimes coming in the evening. And it was Kepler, I think, who then said, this is the same star. This is Venus. The morning star and the evening star is the same. So to be identical is the only universal relation that exists, and to extend logic with this relation is okay. But if you start to say, I have another symbol that you should interpret in a specific way, then things become very difficult. For instance, the number of models of structures where you can ask questions is reduced. Typically, if you say there's a symbol called order, something is A is smaller than B, but then you need structures where order exists. And if you say, aha, I take first order logic and this symbol is order, and then you want to do the usual stuff of logic, first order logic, you are punished because nothing holds anymore. If you interpret something specially, you are lost. But still, temporal logic does it. There's two symbols, and they interpret them differently, especially, and that drastically reduces everything to special structures. And to what kind of structures? Well, not by chance, to transition systems. So suddenly we can interpret temporal logic, certain kind of formulas in transition systems. Okay, and so you see it all fits nicely together. I could tell you that this temporal logic stuff arose within logic in the 1960s with the same two operators with same properties but completely differently interpreted. That they said it's possible that and it's necessary that. And for a big surprise came out that what we now do in temporal logic, we say eventually it will be the case that, and always it's the case that, and the rules of these operators are exactly the rules that also go with it's possible and it's necessary that. Very surprising. So temporal logic is not just any logic, it has deep classification in the logic world. And I will speak about this later on. Yeah, model checking is the standard analysis technique based on temporal logic. And in hardware, I will talk about this later on. In hardware, nowadays, everything is model checked and proven correct with this technique, which I will go into details later on. Theory proving is the more traditional technique to cope with temporal logic, and I will relate it to model checking also. Certification, that's an issue that I'm sure you have never heard about. And this is an idea that I find so brilliant. And I don't understand why it is not so much widespread, I think, as it deserves. So the two things that I think deserve much more attention is abstract state machines and certification. And I'll tell you what certification is. With an example, it was suggested by Kurt Milan from Max Planck Institute in Saarbrücken long ago, not so long, some years ago. And I tell you just one example that you see the point. It has nothing to do with our world, but it's a nice example. So assume you have a big graph, represented somehow as a tape in the computer or on paper, it doesn't mind. So a big graph, either undirected graph, and the graph may be planar or not planar. And you know what planar means? You can draw the nodes on the plane in such a way that the arcs don't cross. Okay? So some graphs are planar and others are not. So given as a list of arcs, you have no idea how to decide is this one planar or not. Now what would man do? What would usually classically in science be done? You write a program that decides if the graph is planar or not. So you put in your big graph and the output is yes, or the output is no. And what have you to do? You have to believe it. You have no intuition. Why is it true? And how could I assume you thought it's certainly planar and the output is no, it's not planar. Then you would like to see a reason or to get an intuition, or you may think maybe this program is wrong because I'm so convinced intuitively it is planar. And he says no. And I want to have, so to speak, a witness, an argument why the output is true. Okay? So what would be a good witness? Well, in case of planarity, it's a simple thing. You just get a drawing of the graph that is planar. Okay, then you only have to look, is all the nodes, are all the nodes represented, are all the arcs represented, and is the drawing, is the distribution of nodes such that the graph is planar, and then you are personally happy, yes, the output is true. Because this is a good witness for planarity of your graph. It's a planar representation. It's more difficult if the answer is no. So what would be a good witness to convince you it is not true? And assume the program is smart enough that shows you a very small subgraph, and it's a subgraph with 5 or 6 nodes. I don't go into details. And it shows, look at this small subgraph, these 6 nodes, and all the arcs combining them. And the program says, already this small graph is not planar. And if the small subgraph is not planar, of course the whole graph is also not planar. So now you have got a witness, and you have now only a smaller problem, namely to decide, to convince yourself that this small graph is not planar. Well, there's a famous theorem that it is not planar, and if you don't believe the theorem, you can play around, and after 2 hours you are convinced it's not, because with 6 nodes you can play around. So what was my point? The result of the program was not just the result, but also a way to convince you that it's true. And if we have customers in our area who would want to be convinced that what we do is correct, then we need this kind of witnesses. Okay? So this, I think, was a beautiful example to show that intuitive witnesses are really useful. And the question is, we find always witnesses for any kind of algorithms? And the answer is, so it is in some cases more or less simple to do this kind of intuitive witnesses, in other cases, of course, not. But I think it's worthwhile to push this kind of research, to continue this kind of research. Okay, next point is invariance. So, as I said, I'm interested in behavioral models, so something changes. So let's go to the principles of science. So what is physics and what is chemistry about? In a way, it's about invariance. They say, okay, the world changes, but something remains constant. And to find rules of nature is to find invariance. So an example is the notion of energy. We all have an intuition what energy is. Why don't we have this intuition? It's a very, very difficult notion. How can it come that you say, okay, we have 2 liters of gasoline, and this is more or less the same as something, not 2 liters of electricity, or you can move with this something. So we have a law of energy equality, so if no energy is supplied, if nothing goes in, nothing goes out, then something remains constant. And this kind of invariance is what governs real science. So do we have similar invariants in informatics? And the answer is, well, a little bit we have. For instance, some of the elderly of you still have learned how to verify programs with Hall logic, resistant thought. Some know Hall logic. And Hall logic invariants are, of course, invariants in this classical sense. But they are a little bit trivial. So we are interested in big systems, and we should be interested in much more involved invariants. And I'll give you an example. So we have a banking system, and you go to the machine and put some money from your bank account. Of course, you expect invariant, namely that the sum of money that is on your bank account before you do it, and the sum of money on the bank account plus in your hands is invariant, is the same. Okay? And we have to make models that would allow to prove this kind of invariance. And maybe there are even more complicated invariants. And informatics should look much more about interesting and non-trivial invariants, of which Hall logic invariants are just the first step. Okay? And I can tell you another story in this context. Pensioners have a much more expressive form of invariance. And one can ask, why are pensioners invariants more expressive than Hall logic invariants? And there's a deep philosophical reason behind it. That is, if you may have an assignment statement, for instance, x becomes 3, then at the end, you know x is 3. And then if you look backwards and ask, what was the value of x before, you have no idea. Okay? Now, in a pensionate, if you have reached the state, and you know this transition has made to reach the state, then you can compute backwards and can recompute the original state. And in Hall logic, as you know, you always argue backwards. So arguing forwards and backwards is helpful for invariance, and pensionate transitions are simple enough to have this kind of information loss transformation, and therefore the invariants are more expressive. Okay, well, simulation. You have a system and you want to simulate it with another system such that the important properties are retained. The classical way of refinement or simulation. And I will talk about simulation later on, and about a special kind of simulation which is called bisimulation, and which is much more important than simulation. And I will give you an intuition why bisimulation, this in first class so technical, strange thing, why is it so much more important than simulation? This is also one of my points later on. Refinement checking. You want to refine a model, and you want to say, upon refinement, properties are preserved. That's what we want in refinement, and we should make our modeling techniques such that this is easily done, which is not yet the case. Structural analysis, well, this is the first point where you would exploit the technical structure of your modeling technique. In pensioners, you have a lot of structural, you can say this kind of subgraphical structure of a pensionate. If this exists and this is that property, then the whole pensionate has a property. And other structural techniques exist. But this is the only technique that strongly relates or strongly is based on the technical structure of the models. So what I want to say on all this lecture is that structure, the technical details here should not play the central role. You should not fight over, you take this or that technique because its syntax is like this and that makes no sense. So it's the deep ideas behind it. That's what I like to talk about. Okay, design. The idea is that we design systems that are correct by construction. So you have an intuitive idea what your system should do, and you write it down. And that is, of course, correct what you write down, simply because it meets exactly your intuition. You may specify some additional properties and then verify that the model really has these properties. And then it is correct by construction. The compositionality, that is, I talk about this later. Well, control composition is you have two models, and then you compose them, and then you ask what is the property of the composed system. I come to this. Stepwise refinement, that is one of the fundamental ideas of also TLA. You start with a logical specification, you refine it more and more, and TLA gives you rules how to refine. And at the end you have still a logical model, but it almost looks like a program. You have assignment statements on the left, you have a variable, on the right you have an expression. It looks like a program, and then the idea is, take this program, let it run. And the way you gained it was by small steps which are easy to prove to retain the important properties. Okay? Yeah, now come the two important things why Focus and TLR have found their place here. Implementations, implication. So if you have a specification which is a logical term, for example, or whatever, logical expression, and you have a more refined logical expression which you call then the implementation, then the relationship between those should be an implication, logical implication. And don't make the usual mistake, the implication goes from the implementation to the specification. Okay? The specification requires you to do something. The implementation chooses out of the many possibilities one, and that means that the implementation should imply the specification. So to give you an example, specification says do A or do B. Now you implement it, and you implement it saying I do A. Okay? And then of course A implies A or B. I insist on this because usually one has the strange idea that implication should go from the specification to the implementation, but it's wrong. The implication goes from implementation up to specification. Think about this. It takes a while to accept it. Composition is conjunction. Well, this is what this focus stuff we try to do. So you have two components. Each component has its relevant properties. Now you have an easy operator to compose, and the compose system has also properties, and those properties should be more or less composition of the properties of the components. Does it function? Well, almost never. But one of the attempts to make it function was this focus stuff, and I think it's worth to follow this, because many mistakes occur upon composing software components. They are the mistakes. And if you could control this much better, then it would be helpful. Okay. Now I have given you a lot of specification techniques that are not so specific for service-oriented architectures. So now how are all this in the background related to service-oriented computing? Well, it was said already several times in this meeting. The first part is we have loosely coupled systems. So in the classical world, we have no assumption at all about the structure of the system. If you have to implement something, do it. If you have to implement, say, in abstract terms, you have to implement a computable function. And on the structure of the device you do it is not discussed at all. Whereas in our world, we say you should not just implement a computable function, but you have given a certain structure of components and they communicate asynchronously, etc. So you are given a structure and you have to do your computation on this structure. And the second point is you're interacting while computing. And this is a very crucial point. So in the classical world, you compute a function. That means you have an initial state where you are given the input, and then you compute for a while, and then you stop, and then you produce the output. That's classical computing. And here we do interact while we are computing. It is theoretically a completely different approach. And we will see how deeply this difference will go. For instance, this is the third part. As you interact with your environment while you are computing, it's reasonable that computation runs forever. In our world, infinite computation is what we want. Whereas in the classical world, where you compute a function, infinite computation is a failure because you get never any output. So you are running it in a loop forever and you get never output. Yes?
So what do you mean with interacting while computing? Is this you have deployed a system and then you still change the components or whatsoever?
No. No. Give you an example.
Yeah.
A service is running. The service is fixed and it's running. And in each step, in some steps, it expects an input, and the next step it gives output. And there's another service that provides the input and accepts the output. So while the system is running, one computation is going on. In each step, there may be interaction with the environment. So if this goes on infinitely long, that's perfect, because it makes sense, because you are constantly interacting with your environment. In contrast to the classical world, where you have no interaction while you are computing, so initially you have input, and then somebody stands beside and waits until you finish. And if you never finish, it's senseless. And not finishing computations would never be distinguished. You can say this computation is infinite in a different way from that, because you can observe it. But if you make anyway steps which compute, which interact, then you have infinite computation in a completely different world. Okay? Fine. So for many aspects, classical theory simply does not apply. There's nothing wrong with the classical theory, of course. It is wonderful for its world, but it's not the whole world shaped like the assumptions are in the classical computation model. Okay, so when I said today and tomorrow, I will give you some highlights of all this. In fact, it will be tomorrow, not today and tomorrow, in the afternoon. At 3 o'clock in the afternoon, and I will talk about this area here and about this area here. And why did I choose them? I chose them, well, first of all, they are completely independent of any of these specific techniques. They are valid, so to speak, in our world in general. They are very relevant. There are a lot of implementation of tools, of arguments in this context, and all of you should know this work. And that brings me to the end of this part, and I think it makes no sense to start a new one.
That's right.
So let's start
about now, and thank you very much for this comprehensive overview. So, are there any questions now, or are you just waiting for the second part? Yes, of course.
Just a small question, because I'm curious. So first, thank you. It was quite interesting. I was wondering about your example about modeling the internet. What would be your pragmatism here?
Okay, let's try it. The internet consists of a lot of components. And you can, for instance, your computer is part of the internet, assuming that you're not online. Okay, so you can model your computer, assuming you model your computer. And then the question is, how does this model of your computer fit to the model of the rest of the internet? Okay? And well, if you do it in this interleaving way, so you have to assume the internet without your computer is doing this run, and now you have to squeeze in what you are doing, it makes no sense. So it must be, in the model, it must be an asynchronous model, completely asynchronous model, where you, given a large system, can easily expand it, adding a small component like your computer. And this kind of modeling can be done if you are willing to lose some implicit assumptions, and the most important is the assumption of global time, and mapping everything that happens in your world onto this global time scale.
Other questions?
I want only clarification also reaching question about interaction with the environment. Like we can tell about it. It's like when people we can change something and it's always reflect into the environment directly or not.
I don't want to. I'm not interested in changing the system itself. It's an operating system. An operating system. It is not built as follows that in the moment of installing the operating system you get all the input and then you start the operating system and after 20 years you finish it and give all the output. That's not what an operating system does. Okay? But instead it runs for 20 years and while it's running it's communicating with the environment.
I would like to ask a question about the graphs that you said. You mentioned that the planar graph, it's an easier process to detect that it is a planar graph because we can see the whole image. And you mentioned that it is more difficult to find a non-planar graph because you must take a small portion of the graph in order to detect it.
No, you misunderstood. You have given a graph and you don't know, is it planar or not? And now I said, to make yourself sure, you must distinguish the case. First, assume it's planar, then you get a witness that shows you it's planar. I think that is easy. So you have only to control if the representation is really a representation of your graph. Okay? And then you have to control if no arcs are crossing. So you still have a job to do, but a small one. The first job was to decide, is the graph planar or not? And the system gives you a representation of a graph. And now you have another job. The job is to make sure that this representation is really representing your graph and that is planar. And that's easier than your original question was. And in case the system says, no, it is not planar, it gives you a subgraph of your graph. So you have to control, is this really a subgraph of my graph? It has 6 nodes at most. That's easy to do. And then the system says, this subgraph is not planar. Okay, still you have, either you believe it is not planar or you have now a job to do, namely to make sure, to convince yourself it is not planar. Or to believe a famous theorem, which I don't talk about here. So your original job is replaced by a much simpler one, and you are convinced that it is correct. Okay, to convince yourself, not just to believe that the program is correct. You see, the program even must not be correct. It's not necessarily it's correct for all graphs. It's sufficient if it's correct for your graph. Okay? So instead of verifying the properties of that program, which is a stupid task, you are happy with the witness in both cases.
Just additionally, isn't it a simple process just to detect that small portion? Is it so difficult just to detect that there is a small portion that we have a non-planar graph, so to assume that the whole graph is not planar?
Yeah, it is really difficult. You see, if your graph has 1,000 nodes, you need to visit all subgraphs with 6 nodes out of 1,000 nodes. You can compute how many things you have to choose. I don't think it's simple, and if the system helps you to do that, yeah.
Are there any further questions at the moment? So thanks again for this first part of the report. And we will continue at 3 o'clock.